All right, after having considered dynamic efficiency and user costs last week, we're going to fully dive into the study of non-renewable resources in this week's video. Before we do, I'd like to take a step back and take a broader perspective in terms of what distinguishes resource economics from environmental economics, given that these two are generally lumped together both in undergraduate classes, but also in some of the academic journals in the two fields. So we're going to think about what some of the questions are, which are more pertinent to resource economics than to environmental economics. So some of the key resource economic questions that we're going to ask over the next class and a half here are going to be whether or not the private incentives to exploit natural resources align with social well-being, how we should allocate resource extraction over time, how might we expect natural resource prices to change in the future, as well as some qualitative questions such as whether we are running out of natural resources or how much of our resource endowment we should leave for future generations. So these are, I think, important philosophical and normative type questions, as well as some more descriptive ones as well, which we can answer with more specific statistics. So I know that this is going to not be a popular analogy with some of the environmentalists in the class, but I'm not doing it as a way, once again, to devalue natural resources or the environment, but as a way to think about how we can efficiently manage them over time and align the incentives of the account managers with the incentives of society. And so we can think about natural resources as being like a form of bank accounts, in that their value of the natural resources is going to grow over time if they are scarce. And if that scarcity increases, or if we're extracting at a faster rate than at which those resources can reproduce or grow. And so we can think about depleting our bank account through withdrawals, depleting our natural resources through extraction or withdrawals. And we need to think about how fast to withdraw those natural resources, just like we would think about how quickly we withdraw money from our bank accounts, except for instead of the rate of replenishment of the resources being our deposits or interest rates, we're going to think about the rate of replenishment of the resources as being due to natural or biological processes or replanting. So when we think about efficiently managing bank accounts and natural resources, some of the questions we need to ask ourselves are: how quickly should the resource be withdrawn? How long is the planning horizon? Are we concerned with 5 or 10 years, longer into the future, or an infinite time horizon? And how much should be invested in replenishing that capital, whether it's natural capital or financial capital? So over the next couple of slides, I want to think of a couple different ways of classifying our natural resources. And I apologize, this image just got completely distorted when I converted it to this frame that I like to use for my online videos. But we can primarily distinguish natural resources as either being depletable or renewable. In other words, as being non-renewable or renewable. And within that initial classification, our renewable resources can be storable or non-storable, and our depletable resources can exist in current reserves, in potential reserves, or as the total endowment of that resource. And so this is one way that you kind of branch off different types of resources to classify them. The book has a different way, and I'm going to turn to that next. Well, I guess before I do, I should probably clarify what I mean by some of those terms. And so depletable resource, once again, just a non-renewable resource, which is not naturally replenished or is replenished at such a low rate that it can be exhausted during a relevant time period. Fossil fuels here, good example. The rate at which it's depleted is affected by demand and thereby by price as well as durability and reusability. The current reserves are going to be the resources that can be extracted profitably at current prices. So if we think about oil here, this is going to be oil which exists in more shallow, accessible reserves in the Middle East, in the Gulf, in the Arctic, and at the present time period, I think still at the present time period, in the tar sands in Canada. So the potential reserves are going to be also including, in addition to the current reserves, or in addition to what can be extracted profitably at current prices, the amount of the resource which can be extracted, which we know to exist, which can be extracted in the future based on profitability at that point in time. And so this is higher cost resources, higher cost reserves. And so the resource endowment is not based on price at all, but just represents the natural occurrence of resources in the earth and is a geological concept, whereas current reserves and potential reserves depend on prices. And so the book also uses an example of a McKelvey diagram, and this is slightly different, has a little bit more detail. But overall, this McKelvey diagram is a way of classifying the geophysical endowment of the resources on the earth as having two different dimensions of scarcity, the geophysical scarcity as well as the economic scarcity. And our reserves are just going to be defined by those which are economically profitable, economically not scarce, and that are geophysically available. So there is greater possibility to find economically profitable resources in this top right quadrant, but we don't know if they exist. And there is certainly some of the resource in this lower left quadrant, which we know exists, but would take too high of a cost to extract for us to reasonably consider it part of our reserves given current technology. And so both of these forms of scarcity, the economic and the geophysical, combine to create the total scarcity, which is a feature of our non-renewable resources. So the economic challenge of managing our depletable resources is due to, once again, the finite size of the endowment of those resources, and thinking about how we're going to allocate that resource across generations, kind of like we did earlier in this lecture, but with significantly more than 2 time periods, while ultimately then being able to transition at some point in time to a renewable resource at the lowest discounted cost across all generations. On the other hand, a renewable resource is going to be one that is naturally replenished. Examples being water, fish, forest, solar energy. That doesn't mean that we can't completely collapse stocks of these resources, but it means that there is a rate of replenishment which we need to keep in mind, which will inform our optimal extraction rate. And so some of these resources are going to have their rate of replenishment depend on human activity. Some are going to be more independent. And we could think of the extraction of crops or timber or fish as being those which do depend on human activity. However much fish we extract in one time period is not only going to impact the amount of fish left over in period 2, but the transition of the amount of fish from period 2 to period 3, that there is going to be less of them to reproduce. However, solar energy is renewable, and however much we harvest in one period doesn't impact however much we can harvest in another time period. Some of these resources can be stored, others cannot, and once again, all of this depends on current levels of technology. But the economic challenge defining renewable resources is going to be how we not only think about maximizing the discounted present value of the future stock of the resource given a transition point, but how we maintain an efficient and sustainable flow of the value of these resources in perpetuity. And so over the remainder of the next 2 weeks, we're going to consider a series of rules which will be used to offer best guidance for the management of both renewable and non-renewable resources. And we're going to contrast these best management practices with what may be considered like a more naive, less economically informed series of rules for managing the resources. And so the first intuition or guess for managing non-renewable resources may be to come up with a reserve to use ratio. And so let's say we have a 100 billion gallons of oil underneath the Earth's surface in economically profitable reserves, and we know that we use a billion barrels per year. So this would suggest that we have enough resources to last for 100 years. However, that's going to be misinformed because we're leaving out a couple of factors. One, we're ignoring that in the future, there's going to be a greater marginal user cost created by the scarcity. Once again, the opportunity cost of more extraction now is that there's more scarcity in the future. As it becomes more scarce in the future, prices are going to increase, and people are going to consume less in response to those higher prices. It ignores the possibility of discovering new reserves, and in part that those new reserves and those substitutes are going to be driven by the higher price of that resource due to the scarcity imposed by consumption in the present time period. And so by not taking into account price or scarcity, we are misinformed about how long we can expect that resource to exist. So a more nuanced way of thinking about this is going to be using the hoteling rule. So the hoteling rule is going to state that our optimal extraction path of a non-renewable or depletable resource is going to be such that we extract so that the rate of change of the marginal user cost of that resource divided by the marginal user cost of that resource at any point in time is equal to the rate of interest. And so this is basically a no arbitrage condition, basically saying that we are not going to be made better off by leaving more of our resource in the ground, and we're not going to be made better off by extracting more out of the ground. So if our left-hand side of the equation here was less than our right-hand side, and the marginal user cost of our resource was less than the rate of interest, then that would provide an incentive for us to extract even more of it because it's less valuable in the ground than extracting it, selling off our profits from that resource and investing it at that rate of interest. And so we would then extract more, which would increase the user cost, which would then bring it more in line with the rate of interest. And if we extract too much so that the marginal user cost is going to be greater than the rate of interest, the left-hand side is greater than the right-hand side, then we're going to slow down our extraction because it's going to be gaining more valuable. That resource is going to be gaining more value in the ground unextracted than if we were to extract it and invest that money in an interest-bearing account. And so it's self-correcting. It's a no arbitrage condition, but it should be an arbitrage just means that we can't buy low somewhere, sell high somewhere else. There's no opportunity for exploiting profit by trade there. And so that should be how we guide our decisions about the rate of extraction of a depletable resource. However, this simple rule is going to be based on a series of assumptions, and not all of which are always likely to hold. The first assumption is that there is a private owner who owns a complete stock of that natural resource. The second is that the complete stock of the resource is fully known and there is no more. The third is that once some of the stock is withdrawn, the resource withdrawn is used completely with no waste, leaving nothing over for reuse. Fourth is that the stock can never regenerate itself as a true depletable, non-renewable resource. The fifth is that the cost of withdrawing a unit of the resource is always the same. There's that constant marginal extraction cost. And going forward, to make things really simple, we can just assume that that cost is constant at $0. And lastly, that there are no alternatives to that resource. There's no backstop technology that could replace it. And so these are obviously highly restrictive assumptions. But just like in a basic supply and demand model where we're relying on the assumptions of perfect competition, which are not very likely to hold in most settings, we can still learn something about the optimal extraction rate of a non-renewable resource by following the hoteling rule and knowing that there are limitations, that it's not going to provide us with the exact right answer if these assumptions aren't met, but it's still going to be informative. So even though our marginal extraction cost is constant, our marginal user cost is going to increase over time as we extract more out and there's more scarcity. And so our total marginal cost, being the sum of the marginal extraction cost and the marginal user cost, is going to increase over time. And because of that total marginal cost increasing over time, our quantity extracted in each time period is going to decrease until eventually we don't extract any of that resource at a given time period. The question is, does that point come when we fully exhaust the resource? Maybe, but in general, that point at which we no longer extract any of the resource is going to be a product not of the amount of that resource which is available, but of the choke price. And so as costs rise, quantity extracted falls over time. This is just like our law of demand, right? But if we're moving from right to left on this graph, and we're starting off with having a relatively high quantity of tons per year, and that quantity decreases as the real price increases, then eventually we'll hit a choke price. And that choke price is going to be the price at which it's no longer profitable to extract any of that resource, and is going to set the demand and supply equal to zero for that resource at that price. So if we have a renewable substitute or a backstop technology, then there's going to be a smooth transition to exhaustion or to that the use of that renewable substitute. And the point at which we switch from a non-renewable and depletable resource to a renewable substitute is going to be called a switch point. And at that switch point, the total marginal cost of the depletable resource, being the marginal extraction cost and the marginal user cost, is going to equal the marginal cost of the substitute. So here we have, once again, a constant marginal extraction cost in an increasing total marginal cost as we deplete more and more of the depletable resource the user cost is increasing until eventually the sum of that user cost and the marginal extraction cost equals that constant cost of the renewable resource. Similarly, we'll look at how much of that resource we can consume over time. And in the initial time periods, we're consuming high amounts of the non-renewable resource until eventually we hit that switch point, which is identified in graph B, and we make the conversion over to a constant stream of renewable resource extraction. So there is still an assumption which we could even further relax from the basic hoteling model, and that is the case when marginal extraction cost is not constant but increases over time. And this makes sense that if we are extracting the resources closest to the surface or that are most economically profitable, and we exhaust those, then we start reaching further for those suboptimal economic reserves, and it's going to cost more to extract those resources. And if that's the case, then the marginal user cost is going to decline over time and eventually reach zero at the transition point. And the resource reserve is then not going to be exhausted, and some's going to be left in the ground because it's too expensive to take out. And this is, once again, where that choke point comes into play, that the point at which we no longer extract any of the resource isn't necessarily when it's completely disappearing or completely depleted, but where the price of extracting any more is too high. And so we can also think about the marginal cost of exploration, of trying to find new reserves, and that's going to be expected to rise over time as well, as we would think that we have, once again, identified the lowest cost reserves first, and maybe it's going to take more of a cost to find any additional reserves. And the successful exploration of finding further reserves would then cause a smaller and slower decline in consumption while dampening the rise in total marginal costs. And so once again, here looking at B, we can see that when the marginal extraction costs rise over time, the total marginal cost stays relatively more constant, and eventually that user cost, the difference between these two curves, goes to zero at the switch point, where the marginal extraction cost is going to equal the cost of the renewable resource substitute. And we can see a more smooth transition from the extraction of the depletable resource to the consumption of the renewable resource happening at that switch point. Now, when we think about the role of discovery, exploration, technological improvements on the marginal extraction costs, price, and the total rate of extraction, we're going to have two competing effects. So we are going to have a stock effect, which is going to drive price and marginal extraction costs up as the total reserves decrease. But if we engage in technological progress and discovery and exploration, that's going to make extraction relatively cheaper over time. And so we can see the price and the marginal extraction costs decreasing as we engage in more research, discovery, and exploration, except for eventually there's going to be decreased returns on exploration and discovery and technology. And so eventually we're back to that original world where we've identified all of the known reserves of known and unknown reserves of the geological endowment of that resource on Earth. And at the end of the day, it is a problem of scarcity of finite resources. And so limited supply, and if demand continues to increase, and the marginal extraction cost and the price are going to increase as well. And the actual rate of extraction is going to follow just an inverted relationship where it's initially low due to the higher price and extraction costs, and extraction increases over time as more of the resources discovered and the price decreases, and then eventually we've identified everything we can, and we've advanced technology to the furthest point possible, and extraction decreases over time as the resource becomes more scarce. And so we've got a lot of different factors which play into the optimal path of resource extraction for a depletable resource here. And so due to all these complexities, there's no sort of question that I'm going to ask you to calculate the optimal extraction path for a depletable or non-renewable resource. I just want you to understand qualitatively how that extraction would change in response to the inclusion of a increasing marginal extraction costs or the existence of a renewable substitute. One other wrinkle that we could throw in here would be that of environmental costs. And so, as we know from the previous slide, as the costs increase, the quantity extracted is going to decrease. And so, if we include the cost of an externality of there being an environmental cost due to the extraction of a natural resource that we could then impose upon producers or have them internalize, then including that environmental cost would result in higher prices for that resource, which would dampen demand, meaning that we're going to have a longer period at which that resource can be extracted, since we're not extracting as much in earlier time periods. But from the supply side, this is going to cause a transition point, a switch point to that renewable resource sooner, because the extraction costs are going to the total marginal costs are going to increase at a faster rate given the environmental costs. And so whether the inclusion of environmental externalities is going to lead to a longer duration of keeping of the resource by keeping more of it in the ground, or a earlier transition to a renewable resource due to that transition to the switch point being accelerated due to the total marginal cost being higher, is going to depend on the shape of the marginal extraction cost curve and whether that's constant or increasing as well. So there's a lot of ways in which the transition to a renewable resource or just the optimal extraction rate of a non-renewable resource can be impacted. But hopefully you can see how these are all different from that naive kind of rule of dividing the total amount of that resource by the annual rate of extraction as a way of predicting how long that resource is going to exist. So really that's all I want to discuss for non-renewable resources, and next week we're going to move on to discussing renewable resources such as forests and fisheries. So thanks for your attention this week, and look forward to seeing you in class on Monday.